do today is we want to be able to distinguish between intramolecular forces and intermolecular forces. Okay? Hopefully, right here is doing it for you. These are all intramolecular forces, whether it's ionic, covalent, metallic. Okay? Inside the substance is intramolecular. Okay? Inside the substance is intramolecular. In terms of intermolecular, that's where we start talking about hydrogen bonding. Okay? Dipole-dipole interaction. London dispersion forces. Remember those? Okay? Because intermolecular forces are between molecules. Okay? From one molecule to another, the attraction that they feel between the molecules. All right? If you're a polar molecule, you've got a positive end and a negative end. Well, you can attract another polar molecule because it's got a positive and a negative end, right? So you can interact with those other molecules with intermolecular forces, okay? And that's why we identified these as being polar or non-polar, because that's where we're kind of building off of the Vesper shapes and the bonding stuff that we did last unit. We need to be able to see, okay, do we have a covalent compound or an ionic compound? If it's covalent, is it polar or non-polar? Okay? Because that's going to determine the polarity of the substance is going to determine whether or not that substance has a lot of intermolecular forces present or just a little bit. Okay? All right? Or just a few forces. Okay? And then we want to be able to look at a substance and tell what intermolecular forces are in there. Okay? Because if it's polar, it could be dipole-dipole, and it could also have hydrogen bonding maybe. All right. If it's nonpolar, it only has London dispersion forces in it. Okay, and we'll talk about what those are today. All right, so let's knock off the first objective here down below, talking about just different states of matter. Okay, and hopefully these are just a total complete review. All right, in terms of, okay, this is what a gas does. Its particles are moving fast. It's compressible. It takes the shape of its container. Blah, 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 blah. It diffuses throughout its container, that sort of stuff. Okay? Liquid, same sort of deal. And solid. So it's just basically talking about particle movement, right? So gases move the fastest. Liquid's a little slower. Solids hardly moving at all, right? They're just sitting there and they're stuck in their place, but there's still movement in that molecule, right? There's still vibrations and things like that, and all that sort of stuff. And they're not compressible, all right? They don't flow like a liquid or a gas would and things like that, okay? So which of these states of matter has the most attractive forces between the particles then? Solid, liquid, or gas? Where is there the most attractive force? Solid, yeah. All right, and a solid, okay? Remember, with a gas, in terms of kinetic molecular theory, the particles are moving so fast, we're assuming that they're not even having any interactions between gas molecules. Okay? All right. So here we go. Inter versus intramolecular forces. Okay? Intermolecular forces within a molecule. All right? So covalent bonding, ionic bonding. I'll even throw metallic in here, metallic bonding. Okay? Those are the three intramolecular forces. Okay, so in terms of intermolecular forces, okay, those are ones where they're between molecule to another molecule. Okay, so for example, I think these kind of these pictures do a really good job of this, especially these two right here. This guy right here, right? You can see that we have, in this substance here, we've got HOH. Right? Those solid lines represent the covalent bonds, the intramolecular forces. So I'll put those in green. All right, those are covalent bonds in this molecule. Those are the intramolecular forces. The dotted line is the hydrogen bond. Okay, remember though, it's drawn as a dotted line because it is not a bond. All right, it is not a bond like a covalent bond or an ionic bond. All right, it is just an attraction between the positive end of one molecule and the negative end of another. Okay. All right, so something to think about in terms of strength of these intramolecular are much greater in strength than inter. And I should say, I should probably do this. Move that over a little bit so I can do this.
Ooh, I like that.
Okay. Intramolecular forces are much, 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 much greater in strength than intermolecular, than the strongest intermolecular force. Okay. Period. End of story. All right. So, for example, down here at the bottom, we got a couple questions for you. Right. What happens to the particles when we melt ice? What happens to the particles when ice starts to melt? Oh man, not everybody at once now. Come on. They're spreading out. The hydrogen bonds break. So what? So ultimately, just really simply, they're spreading out because they're what can they do now? They can move around now, right? Okay. All right, they start to move around. What about when we melt sodium chloride? What's happening there? What's happening when we melt sodium chloride? Same thing, right? Particles start moving around. Hey, but there is something that's vastly different here. When you put table salt, you can even put table salt on your stove and turn it on high. Okay? Nothing happens to it. It just sits there. Okay? So like when you go to make a grilled cheese, this is my little cooking tip for you. When you go to make a grilled cheese, put a little bit of salt in the pan and then throw the grilled cheese in. Boom. Another level of grilled cheese. Okay, but you can put the...
How much salt? Please tell me that's recorded.
Of course, you have the butter on the bread. Okay, you put the salt in the pan, throw the grilled cheese in there. I'm telling you right now. No, that's way too much. Just let it shake, and then you're good.
That way it's even more.
That sounds pretty good. All right, but hey, here's the deal though. To melt salt, we're talking approximately, I want to say it's somewhere around 1,500 degrees Celsius. Okay, to melt salt, I think. Right? We know to melt ice, you just have to have it at 0 degrees C, right? Okay? 0 degrees Celsius to melt ice. Okay? We're doing the same thing here. Particles are now able to move around from a solid, now they're in a liquid. Solid to liquid, right? But very different forces to overcome here. Forces overcome when we melt ice. When we melt ice, what force are we overcoming? The intermolecular force. Okay. Okay, only the intermolecular force is overcome when we melt ice. Okay, but when it comes to the sodium chloride, we're talking about breaking, right, loosening up these ionic bonds, which are intramolecular. Okay, so in this one, intramolecular forces are overcome. Okay, so that's why it takes just that much more energy to break an ionic bond, okay, in comparison to an intermolecular force, okay, like a hydrogen bond, for example. Okay, not even close. All right. All right, so for example, just in terms of, I'll put relative strength and type of bond here real quick. Ionic, covalent, H bond. These are very general. Dipole, and like molecular, and LDF, London dispersion force. It's kind of, it's very general. It's probably, the scale is not all that great. But
So it takes more energy to break an ionic bond than a covalent bond?
yeah.
So why is diamond have higher melting point than like salt?
They're not, this is just relative. Just relative. Yeah.
Okay.
Yeah.
So it's easier to break the first bonds of water than it is to break the first bonds of salt.
Mm-hmm. We could plug the, right, we can do electrolysis, no problem.
Yes. I feel that less. Okay, yes, that makes
Right.
sense.
Or you take the same thing and you plug it, you know, you shove it into the salt.
Kind of just a lot more covalent bonds?
I think it's this, like the geometry plays a role.
Yeah, okay.
Yeah, and then I'm sure you can talk about like lattice energy. You know what I'm saying? Like how there's variable amounts of lattice energy between different ionic solids. And obviously there's different types of energy associated covalently with different structures too, like with graphite and diamond, right? So same sort of thing, I'm sure. No problem. So very general scale of relative strengths here, okay? All right, moving on to the next page here. You can read the next part, and then we'll get to LDX. All right, so with London dispersion forces here, this of our three types of intermolecular forces, London dispersion forces are by far the weakest, okay? And they are caused by an induced dipole force, dipole force. So we'll talk a little bit about like how that's made up. So the bigger and squishier you are, the easier it is to form an induced dipole moment, and the easier it is for you to, and the stronger London dispersion forces you have. Okay, so we can kind of illustrate this with the periodic table. So if we look at the halogens, okay, our halogen group over here. So as we move from the top of the group down to the bottom, right? Fluorine, F2, right? At standard temperature and pressure, here it is a gas, right? Everything that's red on the periodic table is a gas, everything that's blue is a liquid at room temperature, and grays are solids, right? So when you move from top to the bottom, so we got fluorine has the smallest molar mass. Chlorine, a little bit bigger molar mass, but still a gas. Bromine, big and fat now, and it can have, and it's a liquid because stronger London dispersion forces, okay? And iodine is a solid at room temperature because it's so big and fat. It will do London dispersion forces. So molar mass is directly proportional to, okay, is directly related to London dispersion forces. Okay, molar mass and LDFs are directly related. Okay, so molar mass and London dispersion forces are directly related to one another. So the bigger and squishier the molecule, the easier it is to have an induced dipole moment. So for example, like you can imagine when you bring two molecules together, okay, the electrons on the outside of the molecule, when we bring like charges together, what do? Like charges. Repel. Thank you. Okay, so like charges repel. So that means your electrons, as molecules move closer to one another, the electrons are going to go over to the other side of the molecule and so on and so forth. So you get this one side of the molecule for a split second is negative. The other side of the molecule for a split second is positive. Okay? And that will impact all of the other molecules around it, especially if they're big and fat and squishy and easy to shove electrons around it, okay, to one side of the molecule to the other, okay? So you get this induced dipole moment, which is just a dipole for just a split second, and it's enough to have an attraction for just a second, okay? So, but the bigger, fatter, squishier the molecule, the more, and this is where I can flip to the next page, just kind of brings in the idea of, is it polarizable? Okay, a big, fat, squishy molecule is much more polarizable than a very small, holding on the electrons really tightly molecule. Okay, so polarizability is kind of ability for dipole moments to occur. I should say for induced dipole moment. Okay, so, and remember, just real quickly, a dipole is just a molecule with a positive side and a negative side. Okay, a dipole is just a molecule with a positive side and a negative side. And sometimes those dipoles are just for a moment. Okay, for a second. All right, so you can see here on the table we give you here the halogens, or not the halogens, the noble gases, right? Helium, boiling point, really, really low, okay? Very small, not real polarizable. Very small amount of London dispersion forces, okay? As you move down the periodic table, the atoms become bigger and bigger and bigger, and they're more squishier and fat, and you can move the electrons in that molecule around, okay? So it's more polarizable as you move down, okay, the group because the molar mass increases. Okay, the molar mass increases. So you can see the boiling point decreases because it takes more energy, all right, break the LDF, all right, the London dispersion forces between the molecules because they're stronger because of the larger molar mass, okay? There's more London dispersion force with larger molar mass, okay? All right, so you can define the London dispersion forces in your own words at another time. I'm going to keep rolling, okay? And I'm just going to hit the next question here in terms of which substance has higher LDFs, CBr4 or CF4. Both of them are nonpolar, right? These guys are nonpolar. Am I explicit enough in saying that nonpolar substances they can only have LDF forces? Did I say that? I don't know what I did. I think maybe I went through that. If you're nonpolar, you only have LDF forces. Okay? If you're nonpolar, you only have LDF, okay? It's the only intermolecular force you have, so it's all based on polar mass. This also is the reason why, like, butter, vegetable oil, and things like that, some are solids, some are liquids. It's because of London dispersion forces. Okay? Stuff like that. All right, so back to tetrabromide, carbon tetrabromide, and carbon tetrafluoride. Which one has higher LDF forces? Which one has more LDF forces? Suzanne? Yes. Why is that? Correct. Performance. Yes.
You just like add up just BR and then multiply that times 4.
Absolutely. Yep. Just larger molar mass. Okay, next strongest intermolecular force. Dipole. Okay, this is between polar molecules. Got to be polar. Have to be polar. Okay, not very strong, but they are, these are permanent dipoles. Okay, a polar molecule has a permanent dipole. It's got a positive end and a negative end permanently. Okay, so based on electronegativity and its symmetry, right? Because it's asymmetrical. Okay, it's a polar molecule, and you get attraction, just like a magnet, right? The little tiny magnets, positive end, negative end, attracting each other. All right, so they'll cling to each other and form liquids, solids, etc. Right? And mostly that. So, got to be polar. Can't circle that enough. All right, polar molecules, they have London dispersion forces and a dipole. All right, so I just want to point that out. So, like HCl, for example, here has LDF and dipole, but this is the largest contributor. Right? The one that really matters, dipole interaction. Okay, because it has mass, it has London dispersion forces, but they don't really play any role in terms of why HCl clings to other HCl molecules. It's because of dipole, right? It's much stronger force, right? So, for example, right? So you can talk about a couple things down here. So, in terms of these questions here, do nonpolar covalent compounds have dipole attractions? No, but they have induced dipole attractions. Okay, dipole is for polar molecules. An induced dipole is something that's nonpolar that you can induce a dipole moment in for just a split second. Okay, that makes sense? All right, that's the difference between London dispersion and dipole. Of these two substances, HCl or HF, which has higher dipole attraction? Which has a better dipole attraction? How do we know? One of these is a stronger little magnet. It's a stronger positive and negative side. What? HF does, yes, that's true. Why? Great. most electronegative. So, most electronegative difference between the two here. So in other words, it's more polar than the other molecule. The other molecule is polar, but it's not as polar as HF. Does that make sense? Okay, so like if I were to, we got HCl, right? So this side is going to be partially positive, and this side is going to be partially negative. Where HF will be partially positive and partially negative. Okay? More polar of a bond. Remember, these things are a spectrum of being very, very polar to being very non-polar, okay, and everywhere in between. All right, when it comes to polarity, you can be slightly polar. You can also be really, really polar. Okay, all right, make sense? All right, and the very last one, hydrogen bonding. This is the strongest. And just as a reminder, this is an attraction. I can't stress that enough. Okay? It is not a bond. It is an attraction. Hydrogen bonding is an attraction, not a bond. The other key part here is it's a hydrogen that is attracted to, all right, this is a key point here. Hydrogen attracted to where it's on fluorine and nitrogen. Okay? Because that such a polar bond forms very special attraction between the hydrogen and another fluorine, oxygen, or nitrogen. But that hydrogen has to be attached to another fluorine, oxygen, or nitrogen. Okay? For example, CH4 cannot hydrogen bond. Just because the substance has hydrogens doesn't mean it can hydrogen bond. Those hydrogens have to be connected to an oxygen or a nitrogen or a fluorine. Okay, and then that substance can do hydrogen bonding. Okay, so for example, if I have this molecule here, like CH3OH, okay, it has three hydrogens on there, but only that hydrogen there is available to hydrogen bond. Okay, these ones cannot. No hydrogen bonding can form with those hydrogens because they are not attached to a fluorine, oxygen, or nitrogen. Does that make sense? All right, because you have to have that hydrogen. It's got to be very, very positive. The only way that happens is if it's attached to an oxygen, a nitrogen, or a fluorine. Because then the electronegativity difference between the two is large enough to form hydrogen bonds. Okay? So this is the strongest intermolecular force. All right, so down here, why don't you guys give those last few questions a, well, we'll try to get through them pretty quickly here. What is an intermolecular force? What is an intermolecular force? Great. Thank you, Oliver. Force between two molecules. Which is the strongest? Bonding. Weakest? LBF, yep. When dispersion forces, those are sometimes referred to as, AKA van der Waals forces, you'll see too. Sometimes every once in a while they'll call them van der Waals forces. So which will have stronger IMFs? I have to draw these out a little bit. Okay, I have to draw pictures, but I'll. Okay, NH3, two hydrogen bonding. Okay, that's right above here. Here's NH3 right here. All right, where nitrogen trichloride is polar, it's dipole-dipole, but that's not the strongest hydrogen bonding. PF3 or C2H6, okay? C2H6 is linear, right? And it's symmetrical, right? It's non-polar. What forces are present there? LDF only, right? PF3. There you go. What about that guy? It's polar, so I can do dipole-dipole. So PF3 has got stronger intermolecular forces. Okay, so you just line up what the intermolecular forces are. The last one is H2O. We can form two hydrogen bonds. Right? If you do two hydrogen bonds between nitrogen or NH3, you can really only do one. Okay. Woo! That also explains why, like, ammonia boils at, like, I don't know, I think it's 50 degrees Celsius, where this is like 100, right? Because it's stronger, more hydrogen bonds, more intermolecular forces. All right, people. Deuces. Oh, I gotta turn this off. Time to stop recording.